Welcome to Section 6.2, the Entity Relationship Model Overview. Today, we're going to explore the Entity Relationship, or ER, model. This is a cornerstone concept in the realm of database design. The ER model is a powerful tool. It allows us to represent the logical structure of a database in a way that's both clear and straightforward, making complex systems much easier to understand. So, let's dive in to understand its components and significance. Join me as we unravel the intricacies of the ER model and appreciate how it facilitates the organization and manipulation of data. Now, we focus on entity sets in this section. Let's begin with a definition. What exactly is an entity? An entity is a distinct, identifiable real-world object, and an entity set is a collection of similar entities. Entities have attributes that give them unique qualities within their set. For example, in a university database, instructor and student are different entity sets, each with unique attributes like ID numbers and courses. Understanding entity sets is vital for data modeling in the ER framework. They provide a structured way to organize and represent data, enabling efficient management and retrieval. Entity sets can overlap, reflecting real-world complexities. For instance, a person might be both an instructor and a student. This overlap is depicted in ER diagrams with rectangles representing entity sets and lines showing relationships. Such flexibility allows for a realistic representation of individual roles in databases. Let's talk about attributes. These are the descriptive properties of entities. Think of them as the specific details that give an identity to each entity in a database. Attributes can be simple, like a name or an ID, or complex, encompassing a range of information. In a university database, for instance, an instructor's attributes would include their ID, name, and salary, each a critical piece of data that defines who they are within the system. Moving on to relationship sets, these define how entities interact with one another. An ER diagram often uses diamonds to represent these relationships, such as the advisor relationship linking instructors to students. The diagram clarifies connections and lays out the structure of the database. Role indicators further detail these relationships. In some cases, an entity may participate in a relationship in more than one way. For example, in a university database, a course might require a prerequisite, and it can also serve as a prerequisite for another course. Role indicators like course_id and prereq_id mark these different capacities, helping to maintain clarity within the database structure. Lastly, we have descriptive attributes, which are attached to relationship sets rather than individual entities. They provide additional context for the relationships. A good example is the grade attribute in the takes relationship, which doesn't describe the student or the section alone but the specific instance of a student's grade in a course section. Let's embark on a journey through the realm of data relationships, starting with the simplest form, binary relationships. These are the essential links between two entity sets, as clear-cut as the advisor-advisee connections in academia. In contrast, ternary relationships introduce a dance of three partners, students, projects, and instructors, intertwining in a complex choreography, exemplified by the project_guide relationship. Understanding these relationships is key to sculpting a robust database design, one that mirrors the real-world interactions within our systems. Now, let's illuminate the concept of complex attributes. Simple attributes are the single threads, each holding a distinct piece of information like an email address. But when we weave these threads together, we create a composite attribute. A name becomes a rich mosaic of first, middle, and last names. This detailed breakdown, as with an address into its constituent parts, allows for precise data management, from sorting to filtering. It's the composite attributes that give us the flexibility to navigate our data with finesse and specificity. Diving deeper, we encountered attributes categorized by their utility and complexity. Single-valued attributes are the unique identifiers like a student_ID. Multi-valued attributes, however, can encompass a spectrum of values, like the various contact numbers for an instructor. Then there's the elegance of derived attributes, such as an instructor's age, which is calculated from their date of birth, ensuring our database remains evergreen with minimal upkeep. This diversity in attribute categories forms the backbone of data structure, each serving a purpose in our quest for efficient data management. As we bring these concepts into focus, consider the ER diagram that lays out the architecture of our data. An instructor entity is not a mere list but a hierarchy of attributes. From the foundational ID to the composite details of a name and address, and the flexible inclusion of multi-valued attributes like phone_number. The derived age attribute shows our database's dynamic nature, capable of self-updating and reducing redundancy. This blueprint underpins the very structure of our database, balancing detail and practicality. In the final leg of our journey today, we revisit the single-valued, multi-valued, and derived attributes to cement our understanding. Each category plays a pivotal role in how we structure our data. Single-valued attributes stand as sentinels of uniqueness, multi-valued attributes embrace the richness of our complex lives, and derived attributes are the culmination of smart, calculated data management. They are not just classifications. They are a philosophy of database design that prioritizes accuracy, efficiency, and adaptability.